We are going to discuss today the evaluation test MCQs from 21 to 35. You have questions from Unit 1, 2, and some of the questions are from Unit 3, right? So this is our question number 21, and it is from chemical calculations. So we will see how to do the question. There is a small problem with the question also. You should be given a relative atomic masses. Okay, relative atomic masses in order to start the question. But I think I gave that one during the exam. Okay, sodium is 23, then sulfur 32, oxygen 16, and carbon 12. These relative atomic masses should be given. Okay, so now what is the first thing we can do? Now anyone can understand this question. Okay, don't think we can't do calculation. No, it's not something like that. Okay, anyone can understand and start this question. So what are the data they have given? They have given the masses of sodium sulfate and sodium carbonate. So what can we do with that? We can find the number of moles, isn't it? We can find the number of moles of the sodium carbonate and sodium sulfate. In order to do that, we are using this formula. What is the formula? N equal simple M over capital M. Mass over molar mass. For us to do that, we need the capital M values. Okay. So molar masses. How do we get the molar masses? By adding those relative atomic masses. Okay. So for sodium sulfate, 2 sodium atoms, that means 2 into 23, 46. Okay. And there is a sulfur, so 32. And there are 4 oxygen atoms, so 64. 16 into 4, 64. Okay. Yeah. Then you can add them, right? So 2, 1, 142. So 142 is the molar mass of this compound. 142. Okay. Sodium sulfate is, divide this 2.13 grams by 142 grams per mole. Then if you want to find the moles of sodium carbonate, you can do the same thing. You can divide this 1.59 grams by its molar mass. So what is the molar mass of sodium carbonate? There are 2 sodium, so 46, 23 into 2, 46. Carbon 12, oxygen 16 into 3, 48. Okay, so if you add them, you will get 106. 106. Okay, so divide this one by 106 grams per mole. So you can see now it's not clearly seen as divisible because it's not a multiply of 2 or something. But if you think carefully, you can see, I can establish some relationship. The number of moles of sodium carbonate is 0. Now here you will have 1.5 now for the 159. So 0.015 moles. 0.015 moles. And then let's do the same thing for this one. So it's also, we can divide by 2. So things become 71. And now you can see if it is 71, 213, and it is kind of divisible, no? 0.015. So from both compounds, you have this number of moles, and they have make it a little bit difficult with the simplification. It's not clearly seen as divisible, but however, we can divide and see. It means in 100 cubic centimeter and 200 cubic centimeter, you have that number of moles. No? So after mixing, this solution will contain both the compounds. From this one, you have 0.015. From this one also, you have 0.015. But you can see here, they are taking only 1/3 of that. No? So in our theory lesson, we call this taking a small portion out of the total solution. We call that one as separation. Remember, it's a separation. So during separating, okay, during separation, what will happen? Number of moles will be decreased, isn't it? So now here you have 0.015 in 300, but how much will be there in 100? That's what you need to understand. So it's very simple to do. Okay, so you can see 0.015 was there in 300. So how much will be there in 100? So you have to simply divide by 3, no? So 0.005. This is the number of moles of compound that containing each substance. Okay, so from sodium sulfate and from sodium carbonate, you have 0.005. From this also 0.005. That is separation. Okay, during separation, number of moles decreases. You can write that. Moles decrease during separation. And what is this one? Adding water. The final solution is made by adding further volume of water. So that is called as dilution. Dilution. Okay, so number of moles do not change during dilution. Understood? So the same number of moles will be there in this solution. So sodium sulfate and then sodium carbonate, you will have 0.005 and 0.005 here. Okay, so then the question is asking something about the concentration. So we need the concentration of these substances in the final solution. So we have to simply divide to find the concentration, you have to simply divide the number of moles by volume. Okay, so the number of moles is 0.005. Volume is, you can see it's 500, that means 0.5 decimeter cube. So after dividing, you will get what? 0.01 moles per decimeter cube. This is the concentration of sodium sulfate and sodium carbonate. Both have the same concentration. Understand? Both have the same concentration. And then remember one thing. They are asking something about in the question sodium concentration and carbonate concentration also. Sodium sulfate is dissolved to give you 2 sodium plus and 1 sulfate. And then you have sodium carbonate. That sodium carbonate is dissolved to give you 2 sodium and 1 carbonate. So let's say now our concentration in the final solution of each is 0.01. If 0.01 dissolves, this will give you 0.02. And this one 0.01. Here also the same. 0.02 and 0.01. So now the final solution should contain more sodium ions because sodium ions are coming from 2 solutions now, 2 compounds now. So the final concentration will be 0.04 for the sodium ion. Okay, you can do that one simply using moles also, right? Because in the final solution you have each compound is giving you sodium. Okay, so sodium moles will be what? Sodium moles will be addition of sodium coming from each compound. So 0.001 will be coming from one solution. So then 0.02 moles are there from both. Then if you divide this one by 0.5, you will get 0.04 for the concentration. Understand? You can follow that method also. Sodium concentration 0.02 divided by 0.5. You will get 0.04 moles per decimeter cube. Understood? So like that we can say, we can find their concentrations of necessary ones for the question. Statement A, concentration of sodium carbonate is twice as that of the concentration of sodium sulfate. No, it's not going to be correct. You can see now the concentrations are equal. Concentrations are equal. Now, for you to understand this question, this statement is wrong, you don't need to do the whole simplification like I did, Lama. Isn't it? Because you can, once you find out the moles of sodium sulfate and carbonate, you can see they have equal number of moles. No? So when dilution, separation, everything happens, both are undergoing the same change. Okay, so if they had same number of moles initially, their final concentrations must also be equal. They can't be changed. Get the idea? So then final solution should also contain same concentration. Same concentration. Okay, so it's not going to be twice. So A is wrong. Okay, A is wrong. And then the second statement, sodium sulfate concentration is 0.01 and that was correct. And in the third statement, C statement, sodium concentration is also correct. It will be 4 times like the sodium sulfate concentration. Yes, it's true. So how we can get that one too. And then the last statement, carbonate concentration is 0.02. 0.002, it's wrong. However, carbonate concentration is 0.01. Okay, it is 0.01. So you can see now the correct statements that what they're asking. B and C are the correct statements. So answer is going to be answer 2. Answer is going to be answer 2. If B and C are correct, answer is answer 2. So it's a nice question. You have mixing. Here we call this one as mixing. You're adding 2 solutions, mixing. Mixing, separation, dilution. So everything is reminded by this question. You can nicely see the concepts. So in question number 22, they're asking what are the correct increasing order of the given property. So electron affinity, first ionization energy, metallic lattice stability, boiling point. They have given several things. Okay, we'll see the first one, electron affinity. Electron affinity, the given order is correct. Okay, electron affinity, the given order is correct. So A, it says Br, F, and Ca. So electron affinity of group 17 halogens. Okay, it is changing in this way. Iodine is the lowest, then bromine, then fluorine, then highest affinity is there for chlorine. So this one has the highest electron affinity. So that means it is the most likely, the element that is most likely to take the electron. We need to need the reason. Our reason is it is having the optimum size. Optimum size. Understand? It is having the optimum size. That's why. So fluorine is having a relatively lesser electron gain energy, or we can say electron affinity is lower. Why? Because it is a too small atom. It's a small atom. So because it is a small, so the electron repulsion is there. Existing electrons repel the new one. Okay, so that's why their affinity is low. So affinity simply you can understand the likeliness to keep the electron. You have this Cl gaseous atom and take the electron, given electron, and it will become Cl minus, no? So that is called electron gain energy 1, Eg1. Okay, electron gain energy 1. And the opposite of that one, that means Cl minus goes to Cl and electron again. That is called the electron affinity. That energy related to that one is called the electron affinity. Okay, so the same reaction but opposite direction. So let's say during this reaction it releases 345 kilojoules per mole energy. Okay, and in this process it will absorb 345 kilojoules per mole energy. In energy rich lesson, which we will do later, we will understand if energy is releasing, it is called exothermic. Exothermic, right? And if the energy is absorbing like that, it is called endothermic. So same value, but the sign is reversed. Okay. So anyway, affinity, gain energy, both have very close relationship. So try to understand that one. It's basically the same reaction, but to the opposite directions, right? So chlorine is the one that is most likely to take electron because of the optimum size. It's not too big, it is not too small, right? So fluorine, the problem is it is the smallest one from the halogens. So kind of electrons, existing ones are repelling the new one. But the bromine and iodine, the problem is with them is they are too large. So it's very, the new electrons is less attracted by the nucleus. That's the problem. Then look at the second one, B. First ionization energy, fluorine, chlorine, and neon. That's what they have given. Fluorine, chlorine, and neon. So this statement, this expression is wrong. Why? First ionization energy is not going to be higher for chlorine. Why? The reason is fluorine and chlorine are same group elements. same group element. So we should understand downward the group, ionization energy decreases. That means lesser energy is given to remove the electron. So it's easy to remove the electron. You can say become easy to remove electron. Okay. So then the correct order will be the lowest value from these three is for chlorine, then for fluorine, and highest one for neon because it is a noble gas. You have a stable configuration and more nuclear attraction for the neon. B is wrong. Then you can go to the C. In C statement, let's check that one. In C statement, it is telling metallic lattice stability. Metallic lattice stability. Aluminium, magnesium, and sodium. Aluminium, magnesium, and sodium. The sodium metallic lattice stability is not going to be higher. Okay, so this order is totally wrong. It's going to be the other way. Remember, it's going to be the other way. So metallic lattice stability or metallic bond strength, you can see sodium, magnesium, this is wrong, right? Sodium, magnesium, aluminium, metallic bond strength increases. Metallic bond strength increases. Therefore, lattice becomes stable. Lattice stability also increases. So how this happens? The reason is you can see number of free electrons and charge. Then you can say the size of the cation. These are the factors that are affecting. You can see now number of free electrons here 1, 2, 3. They are increasing. Charge is also increasing. Plus 3 charges there, and size should be lower. And here size should be sodium higher and aluminium it is lower. Then for aluminium you can say more metallic bonds in unit volume. More metallic bonds in unit volume. So therefore it's going to be strong and you have more electrons. So always aluminium is the stronger one from these three. You can see, you can understand if you remember the O-level part. Sodium metal can be easily cut with a knife. It's a soft metal. Okay. And aluminium related to that kind of strong, you can't cut like that. No. So that explains you aluminium is better and its lattice is better than sodium. Understood? So C statement is again wrong. Then you can go to the D, the boiling point thing. D. Neon, carbon dioxide, and SO2. So who's having the higher boiling point? Higher boiling point, right? So it's going to be actually correct. It's from bonding lesson. So just remember SO2 is a polar gas. It is a polar gas. And these two are non-polar. Non-polar. So polar gas with a higher mass should have a higher boiling point. Okay, and its mass is also higher. That means it can form more London forces and dp-dp. It is forming dipole-dipole interactions and London forces are also higher. So therefore, it should have the highest boiling point. You can see if the intermolecular attractions are higher or stronger, they can have higher boiling point. And if you take neon and carbon dioxide, this one has a higher mass. Therefore, London forces is higher for carbon dioxide. Okay, so that statement is correct. So this is the order of the increasing of boiling points. So answers A and D are correct. So correct ones are A and D. So answer is going to be answer 4. Answer 4. 22nd answer is answer 4. Right, now let's go to the next question, 23. Out of the diagram indicated below, which diagram is incorrect regarding the Hund's rule? So according to Hund's rule, you can write the electrons are filled to orbitals with same energy in a way that their spin is happening to the same direction. Okay, you can see the first answer A is correct because 1s2, 2s2 are fully completed, right? And then 2p3, you have only 3 electrons. Those 3 electrons should have the spin to the same direction. Okay, so in answer A, it is happening. In answer D also, it is happening. So that same direction of spin should not be always upward. It can be downward also. Understand? So remember the requirement. Spin should happen to the same direction, either upward or downward. Okay, either plus half or minus half, right? Remember? So then A and D are correct according to the Hund's rule. It's very simple, Ramai. This question is very simple. And C and D are wrong. Why? You can see in the C, the middle electron is having a opposite direction spin. So it can't happen. Like I said, spin should be there for the same direction. And then answer B is wrong. Because why B is wrong? First, electrons are filled to maximize the spin with the same direction. That means first electrons are filled 1 electron per each orbiter. 1 electron per each orbiter. Understand? So that's why B is wrong. You must have 1 electron per each orbiter. So B is wrong. Okay, if I say a little bit additional thing to the 23rd question, like this, okay? So according to Hund's rule, so how this P1, P2, P3, P4, these things must be filled. So here 1, like this. First 1 per each, then paired. And here it is fully paired. This is the usual way we drawn. And if I say about this one, these are the other possible ways. You can keep the electrons up in different orbitals also, no problem. This is also correct. And then you can put them in opposite spins also. This is also correct. Try to understand that. Okay, so like that, it can be any place. So now this also, you can write in this way also. This way also, this is also correct. Understood? But filling electrons to same orbitals without having the maximized spin. So this is going to be wrong. Like that, have an idea regarding Hund's rule. It was there in our 2024 A-level MCQ paper also. I think we did that one in the class. They asked a question, what is the answer that is not, that is violating both Aufbau principle and Hund's principle. Okay, so like that, you need to know about these principles. So what are the 3 principles associated with the electronic configuration? Aufbau, Hund's, and Pauli's exclusion principle. Remember what are the rules and how they are written. Okay, you are not asked to write them again, but they can come as an MCQ. No? So then you need to know the rule. Then go to the next one, 24. The correct secondary interactions that exist in an aqueous solution of KCl. Secondary interactions that exist in KCl. Yes. So now if you take the KCl solution, we take a KCl solution, in that the potassium chloride ionic compound is completely soluble. So it will give you K plus and Cl minus. K plus and Cl minus. Okay. So these potassium ions are surrounded by water molecules. The negative part of the water molecule is the oxygen. So it will make attractions or secondary interactions with this one. We call these attractions as ion dipole interactions. Similar to that, Cl minus also can form attractions with the positive part of the water molecule, which is hydrogen. Okay, so this is also an ion dipole interaction. So these 2 answers are there in our answers, right? So in the answer 1, A, it is telling ion dipole interactions between K and water. That's correct. And answer B, ion dipole interactions between Cl and water. That is also correct. Okay, so A and B are correct. So most of the students might miss the question if they didn't remember the part D. Part D, it is telling the attraction forces exist among water. So now this is an aqueous solution. So that means it contains water. So between water and water, between two water molecules, what can happen? What can be there? There can be hydrogen bonds. Between two water molecules, you have hydrogen bonds. So our answer D is also correct. The C is telling something about dative bonds. It's wrong. Anyway, dative covalent interactions are that part is wrong. Dative interactions are not there, right? So anyway, answer is going to be answer 5 because 3 statements are correct. And you can write the definition of dative bonds if you want. Then it will be a complete discussion. Dative bond, simply 2 electrons necessary for the bond are given by one orbital. Okay, and they overlap like a normal one. Right, so that doesn't happen here. No. Anyway, dative bond is a primary interaction. So it's not going to happen. Okay, so that's the answer for the question number 24. It's a good one. And then the 25th one, select the correct statement regarding alpha, beta, gamma radiations and cathode rays. So alpha, beta, gamma radiations, those are the radioactive particles we have, alpha, beta, gamma. And then write about the cathode rays also. Cathode rays equivalent to electrons. Cathode rays are basically electrons. Okay, so let's write cathode rays, electrons. Okay, underline cathode ray and write electrons. And beta particles and cathode rays are having similar properties. Okay, so because they both are electrons. Understood? So now let's see the statement 1. Path of alpha and gamma rays are changed by magnetic field or electrical field. So that statement is wrong, Lamai, because gamma rays are not changing their path as they don't have any charge. Okay, so gamma rays, no charge. So that's the explanation for the first statement. Gamma rays, so no, it is having no charge. So if they have no charge, they does not deflect in electrical or magnetic field. Okay, if they have no charge, they are not going to be deflecting in an electrical or magnetic field. So A is wrong. So what about B? A is wrong because of gamma. Okay, so it says something about alpha. That statement is correct. Alpha, regarding alpha is deflecting. In electrical field, alpha is deflecting towards the negative field, negative plate. That is correct. But what they are telling regarding gamma is wrong. Okay, so you're not going to take that as an answer. Then look at the B. Ionization power of gamma rays extremely low, and it has the speed of light in a vacuum. That's correct, because gamma rays are basically what? Those are electromagnetic radiations. So they will have the speed of light, and since they are electromagnetic radiations, their ionization energy is very low. Okay, photon. These are photons. No? Photons are small, very small particles. They have the particle and wave both properties, right? So therefore, however, it will be very small. So it's very difficult to ionize others. Okay, but relative to that, alpha, it's a very large particle. It's a helium nuclei, right? So then it can ionize gases very easily. Okay, so ionization power lowest for gamma. Then look at the third one. See, when an electrical field is applied on the path of cathode rays, those cathode rays do not deflect perpendicular to the electrical field. Cathode rays are charged, so they will deflect in the electrical field, but that deflection is not happening perpendicular to the field. So let me explain that one. Some of you might have taken this as wrong. Okay, so this one, the telling that do not deflect perpendicular is correct. So here's the way. Now let's say this is our cathode ray. Cathode ray. Okay, so cathode rays are basically electrons now, and electrons are negatively charged. Now this is our positive plate, and this is our negative plate. So where this cathode rays will go? Cathode rays will bend towards the positive plate. And what is the electrical field? Electrical field is along the board. So electrical field, positive to negative, they are not perpendicularly deflecting. So electrical field is along the board and deflection is also happening along the board. So what is meant by perpendicular deflection is something that happens relative to magnetic field. So let's say this is our cathode ray, and if you apply a magnetic field in front of the board, north pole, and south pole behind the board, okay, so what will happen? You can apply the Fleming's left-hand rule and see. Okay, the electrons are moving to the right side, so current is going to the left side. Okay, so then they will move upward. So this deflection is perpendicular because magnetic field is towards the board. Magnetic field is towards the board. This direction. So then that is perpendicular. That's what meant by perpendicular. Okay, so these theories we discussed earlier, but maybe kind of mixed up now. So please go through that. So C is wrong. C is correct. Sorry. Telling that they are not deflecting perpendicular. They are perpendicular along the field of along the electrical field, not perpendicular. So perpendicular deflection is available in the magnetic field. Remember that. Perpendicular magnetic field. Then look at the D. The penetrating ability of beta is extremely high. No, the penetration ability will be extremely high for gamma rays. Now they are in the question. They are asking us to consider alpha, beta, gamma, and cathode rays. No? From those, gamma is the tiniest particle, or basically they are photons. So their penetration power, that means ability to pass through medium, is very high, as they are very small and they have no charge, so they have the highest penetration ability. So telling that beta is having more penetration ability is wrong. Okay, beta has some penetration ability relative to gamma, relative to alpha, but the gamma is the most the one with the most electron most penetrating ability. Okay, so D is wrong. Highest penetration ability. Okay, so answer is going to be B and C, answer 2. Now let's go to the 26th. The molecular formula AX4 has 4 AX sigma bonds and A is the central atom. AX is non-polar molecule and they are asking what are the possible shapes for that. Okay, so the molecule is AX4 and it is telling it is non-polar. So what are the possible formulae for AX4? Now you can give some examples. CH4 is there. CH4 is there. And then you have SF4, XCF4. Like that, there are several examples. I think we had the same several molecules for our another question. So if you take CH4, it is non-polar. It's true. It is non-polar. Because the resulting dipole moment is 0. Dipole moments are cancelling to each other. Tetrahedrally arranged, no, cancelling to each other. But if you take SF4, it's what is the shape of SF4? Remember, it is a seesaw shaped molecule. So now we can see it's not symmetrical. Dipole moments, the result in this not going to be 0. It's not going to cancel out each other. Okay, some part will remain. So the perpendicular ones to the plane are cancelling. this fluorine and this fluorine get cancelled. But the fluorine atoms that are there in the perpendicular, they are in the trigonal planar plane, is not going to get cancelled. So it's polar. You can't say it is non-polar. Okay. And then finally, XCF4, it's a square planar molecule. Square planar molecule. And it's nicely getting cancelled. You can see it's very symmetrical. And here, the resultant dipole moment is 0. So it's non-polar. So then what are the possible answers? It can be square planar or it can be tetrahedral. Okay, seesaw, it can't be seesaw, okay, because it's not non-polar. Tetrahedral is there in answer A. Seesaw is wrong. And C is correct again, square plane. So A and C are correct. A and C are correct. Answer is answer 5. Other combination. So what about this T shape? T shape, the first point is one to have T shape like ICL3. There are no 4 atoms, only 3 atoms. So in that point you can say it is wrong. But however, if you draw that, you can see it's not going to cancel. It's a polar molecule. Polar molecule. And there are no 4 atoms as the peripheral atoms also. Okay, so you don't have to even consider that. So that's why I started the question by showing you these are the compounds that has 4 atoms as the peripheral atoms, because they first says the formula is XF4, AF4, means 4 atoms should be there. It's not a difficult question. Still, these questions can come for your A-level exam also. So study. Now let's see the question number 27. Which of the following statements are correct with regard to NH3 and NF3? Bond pair repulsions are weaker in NF3 than in NH3. So we will first draw the two molecules, okay? NH3, NF3. Now they both are trigonal pyramidal molecules, right? You can see one lone pair is there, right? But the peripheral atoms are different, and the peripheral atom electronegativities are also different. So the first statement they are asking on this is bond pair repulsions. Bond pair repulsions. So now we have to exactly understand where these bond pairs might be. Okay. So since the nitrogen is a more electronegative element, bond pairs will be more closer to the nitrogen. Okay, because why? Because nitrogen is more electronegative relative to hydrogen. Nitrogen is more electronegative than hydrogen. But if you take the other molecule, fluorine is more electronegative than nitrogen. This one has 4.0 value, this one has 3.0 value in Pauling scale. Okay, so therefore bond pair electrons will be more closer to the fluorine. Now what will happen? Consider their repulsion. Since they are very closer to each other, they will have more repulsion. More repulsion. And since they are kind of away from each other, more distance is there. So their repulsion is lower. Therefore, repulsion is low. So what do you think about the first statement? It says the repulsion is weaker in NF3 than in NH3. That's correct. Now look at the second one. It's asking about the dipole moment. Dipole moment. So you have to mark the dipole moments and see. Let's draw the molecule once again. So after marking dipole moments, you can see they all pointed towards nitrogen. And the lone pair also pulling away from nitrogen. So the resultant dipole moment will be upward. Okay. And then here you can see lone pair is pulling, but others are pulling away from the central atom. So fluorine away from the central atom. So kind of they're spreading away. No? So then as a result, what will happen to their dipole moment? It will be low. Resultant dipole moment is low. Understood? Resultant dipole moment is low. So therefore telling that NF3 has a higher dipole moment is wrong. It might be the highest electronegative element, but here the dipole moments are cancelled. You can say it is wrong. You can say dipole moments are cancelled. Cancelled, you can say it's not fully cancelled, cancelled more. Okay, so that's the reason. Then look at the statement C. NF3 has higher bond angle. Now, when you are explaining bond angle, you can nicely go to the explanation. NH3 is having kind of higher bond angle because of the bond pair repulsions. But NF3, bond pair repulsions are lower. So therefore, its bond angle is low. Their bond pairs are located away from each other. So here the lone pair is pushing. So this angle will be 102 degrees. Here you have more repulsion. More repulsion. Like I said earlier, a statement also. Therefore, bond angle is higher. It is having 107 degrees. Both are lesser than the ideal tetrahedral bond angle, but because of the lone pair. But here these two different angles are explaining the effect of the electronegativity of the fluorine, of the central atom and the peripheral atom, how it is affecting the bond angle. It's nicely explained here. Okay, so then C statement is again wrong. NF3 is not the one with high angle, that is NH3. And then last one, electronegativity difference between N and H in NH3. N and H electronegativity difference is 3.0 minus 2.1. 0.9 difference is there. Delta E. So here delta E will be 4.0 minus 3.0. 1.0. So they are having almost, similar, nearly equal. That statement is correct. You can take it as correct. Nearly equal. Nearly equal, okay. Not exactly, nearly. So answer is going to be, the correct ones they are asking, answer is going to be answer 4. Okay, 28. N2O, CO2 goes to Na2CO3. So during this reaction, carbon dioxide is converted to carbonate. Carbon dioxide is converted to carbonate. The incorrect statements, that's what they're asking, incorrect statements, okay? So hybridization of carbon atoms change from sp2 to sp3. So carbon dioxide, this one is sp2, sp hybridized. And our carbonate, iron, this is how we draw it, Lewis structure. And its hybridization is sp2. So it's not sp2 to sp3. It is actually what? From sp to sp2. So the statement is wrong. sp to sp2. So A is wrong. So what about B? Bond length between carbon and oxygen increases. So now here, it was a double bond. It was a double bond. But now here it's not a double bond, and it has the single bond, double bond in between characters. If you take the resonance hybrid of carbonate, you will understand it properly. So there are 3 resonance structures for carbonate, and the bond order is going to be 1.33. Remember? So then if the bond order is lower, so now here you have a double bond, that means 2. Now this is lesser than 2. So if bond order is higher, so lower, and bond length is going to be higher. More length. Or longer. That one is long. So telling that bond length increases is correct. Then the statement C, the product carbonate. All the 3 carbon, oxygen and carbon angles, bonds are equal in the length and angles are 120 each. That is also correct due to resonance. Resonance. The theory resonance you can study and see. The exact molecule is given. So they are exactly 120 because repulsion units are same. And statement D, oxidation state of carbon atom changes. Now, if you find the oxidation state, say the carbon dioxide carbon is +4. It loses 4 electrons to the oxygen. And the same thing happens here also. Oxidation number of this carbon is also +4. So oxidation number is not changing. It is same, staying the same. This is not a redox reaction, that means, no? This reaction is not redox. You can understand that the oxidation numbers of entities are not changing. So now don't be panic and select the answer for B and C. They are asking incorrect ones. So incorrect ones are what? A and D. So answer is going to be answer 4. Okay, 29. Sodium chloride is less ionic character, has less ionic character than potassium chloride. Okay, so let's see first of all whether that statement is correct. Sodium chloride has less ionic character than potassium chloride. So sodium chloride, potassium chloride. So now the cation is same. Cation is same. So that means their ionic character depends on anion is same. Ionic character depending on cation. Cation. So what is our cation? What are our cations? Sodium plus and potassium plus. So sodium plus and potassium plus, if you compare, their size is larger for potassium plus. Okay, cation size is larger for potassium plus. So what exactly this factor we talk about? This is polarization power. So polarization power depends on the size of the cation and charge of the cation. Charge is the main factor, but here the charge is same. Therefore, it depends on size. Okay. So however, polarization power increases with decreasing size and it increases with increasing charge. Okay. So if polarization power is higher, what will happen to the ionic character? It will be lower. Covalent character will be high. Remember that also. Right. So however, our potassium plus has a lower polarizing power according to that. Sodium plus has a higher polarizing power. So then ionic character of sodium chloride is lesser. That's correct. That's correct. Has less ionic character. That one is true. So first statement is true. Now look at the second statement. Now the reason for the first statement is about the cation polarization power. Okay. But look at what is given under the second statement. The anion is larger or has a higher charge. It has a high polarizability. So for anions, you have polarizability. That's true. Okay, that's true. So anion polarizability depends again on the size and charge. Okay, if size is larger, charge is larger, polarizability will be large. That's true. So second statement is also correct. But it doesn't explain the first one. Can understand? It is not explaining the first one. So you have to say about the polarizing power to explain. So this one does not explain the first one. So therefore our answer for the question will be answer 2. Is that clear? So it's a good question. It's a good question. So first statement correct. Second one is also correct, but second one can't explain the first one. If second statement talk about the polarization power correctly, then answer will be answer 1. Okay, so try to understand that question. It's a good one. So the thing is, when the reason I'll tell why sodium chloride is having low ionic character, I'm going to explain it further. So the sodium ion is a smaller one, so related to potassium. So it can easily go and attract the electron cloud of the anion toward itself and repel the nucleus away from that. So because of that smaller size, you can see a sodium nucleus is somewhere here. And it is having a very low distance to the other anion electron cloud and the anion nucleus. So sodium can do that action, the polarization action, very well. That's the reason. It's a good question. Okay. So remember that part. Students are usually getting confused with this one. Okay. I have to repeat that thing. And then the next one is O minus gains electron to become O2 minus. So what is that process? What is the name we can give to that process in the next question? O minus gains an electron to become O2 minus. This one is our EG2, second electron gain energy. What we know regarding second electron gain energy, it is always endothermic. It doesn't matter what is the element. This EG2 is always endothermic. Always endothermic. Why it is always endothermic? Let's say the reason. So it's an endothermic process. So first statement is correct. Why it is happening? Because always negative electrons are repelled by negative ion. That's why. So adding electron is very difficult. Adding electron is very difficult. Understood that? So that's why it is having a higher, the endothermic value. But now let's look at the second statement. 2p sub-energy level being completed by having 6 electrons is a stable state. So 2p6 in second energy level, second or whatever, if it is a p energy level, you have sub-energy level, you have 3 orbitals. So completing that fully is a stable state. Yes, that's correct. So second one is also correct. But can it explain the first state? Can it explain the first statement? No. Explanation of first statement is this one. This is the explanation of first statement. So like that. Now try to understand how I am doing this question. Some of you might have taken the two statements correct, and after that you might get confused how to select. Is it 1 or 2? Okay, so don't get confused. Don't get confused. So when we see the first statement is a correct one, please write a reason with a pencil why it is correct. Then read the second statement. Then if you see a similarity, select answer 1. If the second statement is nowhere near your explanation, then answer 2. That's it. Okay, for that to happen, second statement should also be correct. Okay, right. And the next one, third question or 31, question number 31. The normal boiling point of water is higher than the normal boiling point of HF. Normal boiling point of water is higher than the normal boiling point of HF. That is correct. That is correct. Why? The reason is, now the reason you had to write before going to the second statement. Why boiling point of water is higher? It's a very straightforward fact from our hydrogen bonding topic. Water will have a higher boiling point because it is having more hydrogen bonds. It is having more hydrogen bonds than HF. Because in water molecule, you have 2 hydrogen. Okay, so you have 2 hydrogens and 2 lone pairs. 2 hydrogen and 2 lone pairs. So we can explain that it has more possibility to form hydrogen bonds. There are more other factors affecting, but still we can say it can form more hydrogen bonds. Okay. And in the other one, if you take HF, you have lone pairs more, but you have fewer number of hydrogen. So the ability to form hydrogen bonds, the number of hydrogen bonds that would form by a certain sample for HF is lower. Okay, but relative to that, water will form more number of hydrogen bonds. Okay, so that's better. So understand, answer is going to be, the first statement is going to be correct. And this is the answer. Water has more ability to form, or you can say more number of, the simple meaning, more number of H bonds. Otherwise, the HF will form the strongest hydrogen bond, okay? But still, number of hydrogen bond dominates the strength. So here, strongest H bond. Okay. So now look at the statements. Second statement. Now we know the reason. First statement correct, and we know the reason. Second statement is telling water forms stronger hydrogen bonds when HF forms relatively weaker. Okay, that's wrong. Like I said here, this is the one. So first statement correct, second one is wrong. Answer is going to be answer 3. Answer is going to be answer 3. So why it is stronger? Because electronegativity difference of H and F is higher than H and O. That's why it is having a good strong hydrogen bond. But the problem is with the number of hydrogen bonds. It's a very good fact to remember. Okay, Lama. So any problem on that one? Any doubt? Answer for the question number 31 is answer 3. Sorry, answer 3. Now let's go to the next one, 32. All NO bond lengths of NO3 minus are equal. NO3 minus. All NO bond lengths of NO3 minus are equal. NO3 minus are equal. So that statement is correct. First statement is correct. The simplest and shortest explanation is due to resonance. Due to resonance. Now we have explained this one several times. Okay, so this is the explanation. If I tell you one more time. Now, NO3 minus is a resonance hybrid of these 3 structures. These 3 Lewis structures, or we say resonance structures. And the real NO3 minus, in the real NO3 minus, the NO bond length will be equal. So now you can see the bond order is going to be 1.33, just like for our carbonate. Here it is minus 2 over 3, minus 2 over 3, minus 2 over 3. Okay, so bond lengths are equal due to resonance. Now that's the explanation, okay? Now let's see the second statement. In second statement, it is telling there are 3 stable resonance structures for NO3 minus that are contributing equally to resonance hybrid. So very clear and good explanation. Okay, so first statement is correct and second one is also correct, and explain the first also. Explain. So answer is answer 1. It's a clear answer. Answer 1. Okay, answer 1. Now look at the question number 33. Isotopes have similar chemical properties. Yes, isotopes are having similar, identical, sometimes no chemical properties. Why? Because isotopes are having same electronic configuration. So for the next question, you can see that one is correct. First statement correct due to same electronic configuration. Due to the same electronic configuration, they are having identical properties. Yes. And then isotopes are having similar electronic configuration. Yes, yes, yes. And second one is also correct, and explain the first one. So answer is going to be answer 1. Answer is going to be answer 1, 34, 33, sorry. Is that clear now? Is that clear? So isotopes, what are isotopes actually? Give one example also. Protium, deuterium, tritium, remember? H11, H12, and H13. So they change from the number of neutrons or from the mass number. Actually, it will affect the physical properties, boiling points and other things. But for chemical properties, only during chemical reactions, electrons are exchanged. No, you write that also in your review. During chemical reactions, electrons are involved. So if they have the same electronic configuration, their chemical properties must be same, isn't it? So then add that too. What you are going to adding here? Chemical reactions are involved with electrons. Okay, chemical reactions are depending on the number of electrons, how electrons are exchanging. Electrons are involved in the chemical reactions, not the mass number or number of protons. So they must have the same chemical reactivity. Look at the next question, 34. In question number 34, it says the boiling point of compound. So the two compounds are COOH and OH. Okay, so here, this molecule, you don't need the names here. And the other compound is, they are in the opposite places. So it says the first compound is having a lower boiling point. Okay, so let me explain that. If you take this compound, it is having, if I straight come to the point, it is having what? These intramolecular H bonds. Intramolecular H bonds. So they are kind of decreasing the ability to form H bonds between molecules. This one decrease the ability to form H bonds between molecules. H bonds between molecules. Understood? So therefore, their boiling point will be, so intermolecular attractions will be lower. Therefore, boiling point will be lower. Okay, but if you take this molecule, they are similar groups, these two groups are opposite to each other. So there is a greater chance of making hydrogen bonds with a different molecule than making it with the same molecule. Okay, then making it with the same molecule. So here, these hydrogen bonds are called what? Intermolecular H bonds. Okay, so that's better. So therefore, boiling point is higher. That's the explanation. So first statement is correct. First statement is correct. Now look at the second statement. Second statement says this compound is having hydrogen bonds. It's true. That also is having hydrogen bonds. No? This is also a hydrogen bond. So both are correct. Second statement is also correct. It's not telling this one only has hydrogen bonds. It says this one has hydrogen bonds. Yes, it is. This also has. It's not the factor. It is the type of hydrogen bond. Is the factor. So it can't explain the explanations to a first statement. So answer is going to be answer 2. Is that clear? It is also a nice question. See that again? The reason for having higher boiling point is the intermolecular and intramolecular hydrogen bond. That is the reason. That is the reason. And then go to the last statement, last question. The effective nuclear charge on the valence electron of helium, is 2. That is wrong. Effective nuclear charge is expressed by this equation. ZEFF equal Z minus sigma. Sigma is the shielding effect. And this is your nuclear charge. Nuclear charge. Okay. So all elements except hydrogen has a shielding effect, right there. Hydrogen doesn't have any shielding effect. Okay. Therefore, for all elements except hydrogen, for all elements except hydrogen, ZEFF will be lesser than Z. Remember that. So for helium, it will be less than 2. It's not going to be equal to 2. So telling that there is no shielding effect for valence electrons of helium is wrong. There must be a shielding effect. So I'll explain how that shielding effect is coming. If you take the helium atom, this helium nucleus, and there is only one energy level. According to this, if the electrons are moving like this, now this electron can't shield the other one. But this is actually according to the Bohr model. So Bohr model is not the one we are accepting now. What we are accepting now? Quantum atomic model. According to that, electron location is random, uncertain. So what if this electron come all the way up to here and exists between the nucleus and the considered electron? Then there will be a shielding effect, no? So that's why any multi-electron system, there is a shielding effect. But for hydrogen, you don't have any shielding effect because hydrogen has only one electron. For others, you have a shielding effect. Is that clear, Lama? Is that clear? So that's your explanation. So answer, both the statements are wrong. First one says the effective nuclear charge is equal to 2. That is wrong. Second one says no shielding effect. That is also wrong. So answer is going to be answer 5. That is also a good question. Now you can see there are no kind of easy questions in this paper. For every question, you have a little bit of a tricky point to catch. So that's why I said this paper is a good one. So that's why you need to write a good review for this paper also. And please complete the review of the 35 MCQs and prepare it like a kind of attach the papers together and keep it, right? So that's how we are going to study this properly. So study well and have a nice day.